Welcome to this series of lectures on describing motion of macroscopic objects. So macroscopic objects are objects that you can see with the naked eye and are not as big as stars or galaxies or black holes, and travel at the speed of much less than the speed of light, and can be measured in terms of meters, kilograms, and seconds, and so on. So I'm DHS Maithripala. I'm from the Department of Mechanical Engineering, University of Peradeniya, Sri Lanka. So let's ask this question: what is motion? Mechanics is a subject of describing motion. And before we get into this, let's try to think a little bit about what we intuitively understand as motion. What causes motion? Then how do you describe it? So these are the subjects that mechanics deal with. So let's look at these few examples. So if you look at this Newton's cradle, this is very familiar notion of what we would understand to be motion. When this ball comes and hits this, this other one moves, and so on. So this is very well understood to be what we think of as motion. What about this? No, this is something we all love to watch. Cartoons, and so a lot of funny things happen over here. And for example, this coyote is throwing a rock, and you see it as the whole thing as working as a lever, and so things are moving here. Here also things are moving. Now this is a video of a laser pulse, and it shows evidence of this laser pulse temporally as well as spatially focusing itself. So if you notice, the laser pulse is restricted to a particular region in space, therefore it is spatially localized. And if you notice, it appears and disappears. So the laser pulse is actually also temporally focused. So there's a part where the laser pulse is not to be seen. And so it is going through certain medium. And so this is also, if you look at it, something is moving. Then let's look at this little girl. So this little girl is running around, and this also conforms to our understanding of motion. But there's something else happening here. If you notice the shadow, so the shadow is also moving, and so is the girl running around? Is that motion? And then is this shadow motion? Is this light laser pulse motion? Is this coyote throwing the rock and coyote sliding through this thing? Is this motion? And is this motion? Well, this is pretty clearly motion as we understand it to be, based on our intuition from the day that we have been born. And this girl running around, well, that also conforms to our notion of what we think of motion to be. What about this shadow? What about this? And what about this laser pulse? So are they the same as these balls moving? And are they the same as this girl is running around? Well, if you think carefully, there is a slight distinction between these two. So these balls can cause the motion of a ball, can cause the motion of another ball. The same with the girl. So if the girl goes and hits some object, that object will move. Whereas if the shadow goes and hits another shadow, or if the shadow goes and hits the girl or hits another object, that object, nothing happens. Same here. So this coyote throwing this thing cannot cause anything else to move. So this is something that appears on the TV screen, and it cannot cause any other object to move. Well, at a microscopic level, light can cause things to move. But at a macroscopic level, we all know that we have our experiences that light cannot cause other objects to move. So what distinguishes motion in this sense, in the macroscopic sense, based on our understanding, is that if motion happens, motion should cause other objects to move or change its motion. So motion is something where objects cause other objects also to change its motion. A little more formally said, maybe we can define motion to be the change of position of an object with time. So based on these examples, and as well as our understanding that we have developed from the day that we have been born, we could think of motion as to be the change of position of an object with time. But again, we have to be, so this is fine. This is a very loose and not a precise definition. But how do we make it precise? To make it precise, we will have to observe that these objects, these keywords have to be very precisely defined. What is an object? What do we mean by time? What do we mean by change of position? So without being very precise about these terms, this sentence really doesn't make much sense other than conform to our intuition. So let's look at these three keywords a little more closely. So motion is the change of position of an object with time. So what's an object? So this is actually based on our 20th century, early 20th century realization that everything that we see, these objects that we call macroscopic objects, are made of tiny particles that we call atoms. So a collection of atoms can be formally defined to be an object. That's fine. Now that's very well defined. So it's based on the assumption that everything that we see is made up of particles, and that certain things called atoms, these certain particles called atoms, if you put a certain collection of atoms together, we will call it an object. So what's the position of an object? Let's think about that. So what do we mean by time? Because we want to, so we have realized that motion deals with objects, collection of particles, moving. So what do we mean by moving? It is change in position. What do you mean by change? Well, it has to be something to do with what we call time. So what are they? How do we make it precise? So I don't know whether you have thought about it. If you really start thinking about it, these things can really make you go crazy. But in physics, we try to kind of make precise of what these things mean, and we stick to that definition, and we take that for granted, and we see where our subsequent logical conclusions will take, and we will see whether those conclusions match with what we observe with our senses and so on. And again, I think all of us are familiar familiar with a situation like this, where you are on a long journey looking out of the window, and time seems to stand still, and you seem to be still, but the world around you starts moving around you. So these are things that we associate with motion. And if you really think about it, now this may not be what is happening with respect to somebody that is outside, and so it's so we need to be a little careful when we define what these things are and try to make them a little more precise. So let's think of try to capture what our experience of time is. So we all know that, not that all we know, but our experience is that time is something that can be described by one single quantity, a real number. And we also believe that time is the same for all of us, irrespective of humans, animals, the time is universal. And that we also believe that time does not depend on space, meaning the time difference that 1 second in Sri Lanka is the same as 1 second in Russia, or 1 second is the same on the moon or in the International Space Station. So we assume that time is a quantity that is the same for everybody, and is also the same at every point in space. We also assume that there are no gaps in time. Otherwise, there would be gaps in our life. So we firmly believe that there are no gaps in our life, that our life has been continuously flowing from the day that we have been born. So we have this belief that time does not have gaps or does not have holes. We also believe that time is homogeneous, meaning that it doesn't matter where you initialize your clock, whether you zero the clock now, or whether you zero the clock in another 5 years time, or whether you zeroed the clock maybe 2000 years ago. It doesn't matter. So the time intervals are the same at every point in time. So that's our belief. So 1 second duration 2500 years ago is the same as 1 second duration now. We believe that time is a quantity that is homogeneous. And we also believe that it is isotropic. What do we mean by that? What we mean by that is, so the best way to think of this is something that we all do. We always think about the past. So when we think about the past, we are always thinking that everything moves. If things were moving backward, it would be the same as things would be moving forward. Now, this is a little difficult to imagine, but we tacitly kind of assume that going backwards in time or time travel, time behaves the same way as we would be going forward in time, because forward in time is all we can do, and we have really not experienced going backwards in time, other than when we daydream or when we constantly think about the past. So time is something that is measured by a clock, and if you notice, every clock has some common thing, and that is that you can't really define or construct a clock without motion. So in this example, this wheel is moving, and in this example, the sun is moving. Because of the sun is moving, this shadow is moving. So it is essential that we have motion in order to define or have this notion of time. Again, there's another subtle point here. If you really think about it, what is interesting is, if you did not have a memory, then you would not know whether this pendulum was here now and there in a little while. So if you did not have memory, then there's no way of kind of knowing when then and now is. And that would all mess up this notion of time. So this intrinsic notion of time depends on two things. One is it is motion, but it also depends on memory, where we can clearly define a moment in time and say that this happened then, and this is happening now, and this will happen in the future. So this notion of time is intrinsically meshed in these two ideas of motion itself and as well as memory itself. So if you really think about it, all of these things may be things that are in our head, and it may be in things how we see the universe, and we are trying to kind of put them in a more precise scientific language so everybody can speak in the same language. That is the best way that I think I can think about it, and so maybe you also can think a little bit about it, and you may agree or disagree with it. Similarly, what is our experience of space? Well, our experience of space is that it is three-dimensional, that it is not like a blackboard, that it is not flat. There is this third dimension, and that it is also independent of time. So we believe that this space that you are in is the same. It was 5 minutes ago, and it is the same 5 minutes later in time. So if you go out into the space, that space would be the same at every given time instance, is a fundamental belief that we have when it comes to describing or observing these things that are happening around. So that space is independent of time. And we also believe that there are no holes in space. Otherwise, we would be very careful in where we put our foot. We might fall through it. And so obviously we don't have any such fears, and therefore we believe that space is continuous, that there are no holes. And we also believe that space intervals are the same everywhere. So if you measure one unit of length, say a meter, we have 1 meter of some metal bar, and that metal bar, whether you go and measure it in France or whether you go and measure it in Japan, that length will always be 1 meter. That bar will always be 1 meter. So we have this notion that space is the same. So the space intervals, length intervals are the same everywhere in space. And we also believe that there is nothing special about any of these directions in space. So for example, if you throw a ball in a particular direction, and if you turn 90 degrees and throw the ball, you would expect the ball to behave exactly in the same way. And that is what we observed. If you throw it at a certain angle with a certain speed in one direction, and you throw it at the same angle and the same velocity in a different direction, the ball would travel the same length, same distance, and would take the same time to move. And that's our practical experience. So these are some of the notions that we have intuitively developed from our childhood as a baby, playing with our feet, playing with our legs, throwing things stuff, falling, standing up, running, and chasing things. So this is the experience that we have developed about space and time. So the question is, how do we make these things precise? So these are vague notions that we have developed over years of our life, and but that vague notions are not good enough when we come to describing motion, because describing motion requires some quantitative analysis. What that means is we have to put them into some language where everybody agrees, and that language is mathematics. So mathematics is axiomatically defined, well-defined language where everybody knows what everything means precisely. So if we want to talk about things in an unambiguous way, we better do it using mathematics. So how do we capture these notions in using mathematics? So that is based on these notions that were developed as far back by Galileo Galilei. So how do we describe these things? To describe things, we have to measure, or we have to observe. So we will call anybody who does measuring or who's doing observe as inertial observer. So we will assume. So we start by assuming. So we start by assuming that there are a class of observers called inertial observers. So that is you and me. So we are inertial observers. Such that any two inertial observers will see that all those notions that we had described before hold. Or in other words, to be more precise, time is independent of space. That time is one-dimensional, continuous, isotropic, homogeneous, and the difference in time between any two particular instances is the same. Similarly, space is three-dimensional, continuous, isotropic, homogeneous, and the distance between any two particular points is in space is the same. So this is a fundamental notion that we will take to be true. Now, these may not be true actually, and in fact, we find that these are not true at very large length scales and at speeds that are traveling at speeds that are faster than the speed of light. We know that these are not true. And we also know that these are not true at a microscopic length scale, and where things are happening at a atomic level. But for all our notions of observing through our senses, we have from the day that we have born, we believe in these things, that this fits our intuition. And therefore, we will start by making them or taking them for granted and precisely stating them as assumptions. So let's look at what the implications of these assumptions are. So the next few slides, we will concentrate on trying to figure the implications of these assumptions. So the first thing is, as I was talking about before, this says that there is a universal clock. Because time is independent of space and independent of observers, one can construct a universal clock. And since it is homogeneous, we can zero the clock at any point in time or at any place. And so that clock will be accurate up to an additive constant, depending on where you have zeroed it. So for example, we have taken the Greenwich mean time to be 0. And so it could have been very well Indian Standard Time or some other point in time, point in space. And we also assume that distances, so what this also means, we can rigorously kind of justify these things, that distance, straight lines, parallelism, perpendicular are also universal notions. And that therefore space is what we call Euclidean or flat. So we understand. So we have these Euclidean geometric notions where we start with a point, we start with a line, and we start with what it means for two lines to intersect, what it means by two lines to be parallel, and we go on constructing these notions very axiomatical. So we believe that the space that we live in, these notions hold in the space that we live, or in other words, that the space that we live in is Euclidean. So what does all of this allow us to do? So if the space is Euclidean, we know what it means to be perpendicular. We know how to measure stuff. And so it allows us to pick a frame. It allows us to pick 3 mutually perpendicular axes where the unit length along each axis is the same. And that unit can be 1 meter or some other standard unit of measurement. And so that's the whole point of it. So all these assumptions, if you think about it, tells you that there's that you can pick a frame, and that it doesn't matter really where you put the origin of the frame. It doesn't really matter the orientation of the axis of this frame, and that you can pick them perpendicularly, and you can use this axis to actually describe a point in space. Until you do that, a point in space is just a point in space. It has no way of being precisely described. But what these Galilean laws of space-time allow us is to construct an orthonormal frame, pick the frame at any point in space, orient it in any way possible, because space is homogeneous, isotropic, and so on. And so this allows us to do the following. So what's that? So if you have a point in space, since space is Euclidean, following from the Galilean assumptions, we can fix these three orthonormal axes. And from the point, we can draw perpendiculars. Why? Space is again perpendicular, lengths are known. So notion of perpendicularity is very well known. So we can draw this perpendicular line to the foot of this axis, perpendicular line from this point to this axis, perpendicular line from this point to this third axis, and measure the lengths along this axis to the foot of those perpendiculars. So what does this allow us to do? This allows us to represent a point in a very abstract way as follows. So it allows us to say that this point is x1 units along the E1 axis, x2 units along the E2 axis, x3 units along the E3 axis. Now we can use a little bit of mathematics and put these axis labels in a row matrix and put the measurements along each of the measurements to the foot of the perpendiculars along each axis in a column matrix, and have a very compact representation of the point P using this column matrix X. Now notice, if you change the origin, this column matrix changes. If you change the orientation of the axis, this column matrix changes. So this description of the point P in space is not unique. It totally depends on this frame, this Euclidean frame. And since this Euclidean, the Galilean assumptions of space-time hold, what we will find out is that it really does not matter how you pick this orthonormal frame. As long as it is orthonormal, it doesn't really matter where you put the origin or where you fix the how you fix the orientation. So it basically allows us to identify a point in space with three numbers, x1, x2, x3. So this frame gives you a recipe for identifying a point with three numbers. So mathematically stated, what this means is that a point in space can be identified a triple of numbers, x1, x2, x3. So a triple of numbers now belongs to a very well defined set called R3. In mathematics, you have this ordered set of ordered triple of numbers. Now that is a very well defined notion, because real numbers are very well defined. Ordered triple of real numbers are very well defined. So if you put all possible ordered triple of numbers into a bag, you will call that R3. So now what has this Galilean space-time assumptions allowed us to do? It has allowed us to construct an orthonormal frame, and as a result, associate with a point P three numbers, or in other words, an element in R3. So we have found a way of mapping points in space to elements in R3 using a orthonormal frame. Let's think of 2 points. There's one point P, another point Q. So that point will have three different numbers that describes its position with respect to the three axes, the foot of the perpendiculars to the three axes. Now, so you have three numbers, three ordered numbers or element in R3 describing point P. You have another three numbers, ordered triple element in R3 representing the other point Q. Now R3, which happens to be a mathematically well-defined object, the set of all ordered triple of real numbers, has this nice structure. Or in other words, there are things that you can do with ordered triple of numbers. One thing that you can do is you can multiply these x1 with y1, x2 with y2, and x3 with y3 and you get another real number. So you call that an inner product on R3. Now, what does this inner product give you? Well, it is very interesting. What this inner product gives you is, if you replace y with x, then you get the inner product of x with x is x1 squared, x2 squared, x3 squared. Now we know that by the Pythagorean theorem that what this gives you is the length from O to P. So we call this the norm. So the norm is basically the square root of the inner product of x with x. And that, from a physical point of view, we see from the Pythagoras theorem, gives you the length of this line segment, or the length from point O to point P. So we will define similarly. So we find that if you take the inner product of y minus x with y minus x, you get the length between P and Q, because y minus x, so y minus x is what? X minus x1 minus y1, sorry, y1 minus x1, y2 minus x2, y3 minus x3, the triple. Now you get the norm of that, you get this following relationship. So what is this relationship? We all know from the Pythagorean theorem, that is the distance between the point of P and Q. So what has all of this allowed us to do? The Galilean space-time assumptions have allowed us to pick an orthonormal frame. Now, once we pick an orthonormal frame with any two given points, we can identify two elements in R3. Now, R3 comes with a very nice structure, or in other words, it has this operation called an inner product. Now, using the inner product, we can define the distance between P and Q by the following formula, and it actually coincides nicely with our physical notion of distance between the points P and Q. You can experimentally verify that this is true. Furthermore, you can also find that the angle between, this notion of angle between OP and OQ, the two lines that join P to O and Q to O, are given by this formula over here. So this inner product in R3 is very nice. It gives you a way of computing angles between lines and the lengths of line. So that is what the Galilean space-time assumptions have allowed us to do. So let's again go back and think. So there are two inertial observers. One inertial observer has a certain, so we will call them E and E prime, two inertial observers. A space-time event. So space-time event is something happening at some time, in something happening in space at some given time. Say a light flash, a crack of a lightning, and so it happened at a certain time point at a given point in space. So we need four numbers: the number to represent the time, and the three numbers to represent the position using some orthonormal frame. So I will use a certain frame and a certain clock to represent such a space-time event using the four numbers T and X, where X has three numbers. And there can be another observer, maybe that observer is moving in an aircraft. And so that observer has a different clock, maybe zeroed to some other time zone, and has a different, obviously a different frame that may be fixed to the aircraft itself. And so that person is also observing the same space-time event and making the same measurement based on his or her clock, and making the measurement to the point where the event occurred, using the frame that person uses. So two people or two observers will have two different representations of the same space-time event. So the space-time event is the same, but the quantities that we use to describe them can be different for two inertial observers. But remember, Galilean space-time assumptions tell us that time is universal, that space is independent of time, that time is independent of space, and that they are isotropic, that they are homogeneous and continuous. So based on all these assumptions, what is the relationship? So what do all those assumptions tell us about the relationship between these two quantities? One can actually rigorously show that that these quantities must be related like this. So this can be done, and it's actually in the lecture note that I have provided as a companion for this set of lectures, and you can also find it in any standard mechanics textbooks, especially those treating with relativity. So if you are inertial observers, observers who agree with the Galilean space-time assumptions, so they will have they may have two different measuring systems, but the assumptions imply that their measuring systems should be related to each other by these following relations. So this is T is the shift in time due to the non-synchronization of the clocks. So if the two clocks were synchronized, T is 0. So this A is due to the non-synchronization of the origin of the two orthonormal frames. And this R is due to the non-synchronization of the orientation of the two frames. And we so necessarily find that the two measurement systems should follow a relationship given by this. And this R is a special orthogonal matrix. R belongs to the set of special orthogonal matrix and are constant. So if the two observers synchronize their clocks, choose the origin of the frames to be the same, so synchronizing the clocks, choosing the origins to be the same, and choosing the orientation of the two clocks to be the same, then the two coordinates or two measurement systems should satisfy that given. So let me quickly summarize as to what I have been talking about today and in this part of the lecture. Galilean spacetime implies that there exists a special class of observers called inertial observers who see that time is universal quantity. A special class of spatial coordinates called Euclidean coordinates or Euclidean frames for 3D space exists, so that the distance between any 2 points in space is given by the Euclidean norm as described by me in a couple of slides ago, in an inertial observer independent manner. Any two such observers must necessarily be moving with respect to constant relative velocity with respect to each other. If their frames origins coincided at time t actually, and then their orientations are the same and their clocks were synchronized, then they must be moving with respect to each other at a constant velocity v. So I will conclude this part of the first part of the lectures for now, and we will continue it in a different lecture again. Thank you.